Um, Today we will discuss change of variables. The function f mapping an open set U to an open set V is called a diffeomorphism. Um, F is bijective. F and F inverse both are differential. Let some F be a diffeomorphism from U to V. So let's consider this to be subsets of R power n and subsets of R power n. And let G be a function on V. Call this as X, call this as Y. Now, so Y1 can be written as F1 of X1, X2, and so on, Xn. And Y2 can be written as F2 of X1, X2, and so on, Xn, and so on, Yn, Fn of X1, X2, and Xn. Then integral of G of Y dy such that now G maps V to R. G of phi dy is equal to y is a vector. Y is a vector. Equal to G of f of x times determinant of Jacobian of f y1, y2, and so on, yn with respect to x1, x2, and so on, xn times dx1, dx2, and so on, dx. So this is the change of variables formula. So now Jacobian of y with respect to x is defined as 2f1 of 2x1 and so on, 2f1 of 2xn, so on, dot dot, 2fn of 2x1, and then 2fn of 2xn. This determinant, this is Jacobian and this is a determinant of this matrix. So this is the change of variable formula, and let's solve some problems regarding the same. So we are given x is u squared minus b squared, y is 2uv, and we are asked determinant of Jacobian of xy with respect to uv. Yeah. So let's take, let's compute the Jacobian. So first entry is dou x by dou u, dou x by dou x over dou v, dou v, so u, y, dou by dou v of y. So let's just put it. So this is this, and 2x by 2u, it's going to be 2x by 2u is 2u, 2x by 2v is minus 2v, and 2y by 2u is 2v, 2y by 2v is 2u. And minus 2v. This is 2v, 2u. 4u square plus 4v square. So this is the right answer. So we are given matrix A times UV is equal to X, Y. And we are asked to find the Jacobian of X with respect XY with respect to UV. Since A is an invertible matrix, it's called A to B. 1 1, A 1 2, A 2 1, A 2 2. So X is A11 times U plus A12 times V. Y is A21, this is 1, A21 times U plus A22 times V. Now, Jacobian is 2x by 2u, 2x by 2v, 2y by 2u, 2y by 2v. This is the Jacobian matrix, and as you can see, this is nothing but A11, and this is nothing but A12, and this is nothing but A21. This is nothing but A22. So this is nothing but A. So yeah, first is the right answer. So suppose we consider a coordinate transformation from x comma y coordinates to u comma v such that the Jacobian is 0. then the transformation is not invertible. And this is true. Because let's say there are u and v. This is transformed to x and y. So if this transformation or matrix is not invertible, the Jacobian, which is the Jacobian as we have seen, the Jacobian of x is t, then its determinant is 0. I mean, if it is not 0, then the t is invertible. Let's see another problem. Consider a Euclidean norm and supremum norm on Rn as defined in the following way. And which of the following inequality is true? So let's try to prove this. Euclidean norm of a vector x bar is defined as square root of x1 squared plus x2 squared and so on, xn squared, if they lie in dimensional space. Same time, the infinity norm of this vector is defined as max of mod x1 and so on mod xn. So since this is defined like this, we can say m mod x1 is less than or equal to this infinity norm for all values of x1 to xn, right? By substituting this into this yields inequality. So n times we repeat this. So less than or equal to square root of n times infinity norm. So the last option is the right one. So the relation between infinity norm and L2 norm. So since L2 norm is the max of x1, x2, and so on, xn, this is less than or equal to um, can say that this is less than or equal to this is equal to say square root of precisely equality here, max of x1 square to so on xn square. But this is less than or equal to, since all are positive, and max is less than or equal to max of positive numbers is less than or equal to sum of positive numbers. So xn square. And this is equal to norm x2. So this is the right answer. So we'll solve one more standard example where the change of variables formula is used. Is to find the area of, not the find the value of this integral infinity e power minus x square dx. So there's no closed form integral, that is the closed form value of this integral so that you can get it. So here we use the transformations as shown. Let's compute I square. Right? This I square is, just repeat the same thing. So let's substitute x r sine theta, y is r cos theta, So here we have to use the change of variables formula. So assuming uv to be r and theta, is being transformed to xy, and there is a function g, which is e power minus x squared plus y squared, that is operating on this xy. And um, so let's do it. Let's compute the Jacobian. As we know, this is nothing but say call this as this transformation. Let's call this as f. So g of let's denote x x as f1 of r theta, y is some f2 of r theta, g of f1 of r theta, f2 of r theta, and this dx dy, and we get the Jacobian of xy with respect to r theta, and this becomes derivative. So it's integration over the entire r theta. So if we substitute x sine theta cos theta here, we get e power minus r square, and Jacobian of x with respect to r is sine theta, with respect to theta is r cos theta, with respect to this it is cos theta minus r sine theta. Here we get, can just swap this to be cos theta and sine theta just to be convenient with signs. So we get cos theta minus r sine theta, sine theta r cos theta. Here we get this to be r dr. So now this the radius r varies from 0 to infinity, and theta goes from 0 to pi. So this will yield the simple substitution. We can get this to be, we can compute this. Let's substitute r square to be d. Then r dr is dt over 2. So 0, 0 to 2 pi, and 0 to infinity, where minus t half dt d theta. This is 1, and finally we get half times 2 pi. This is equal to pi. So also note that um, when F is a diffeomorphism, that is, F is bijective, from U to V. Comma F and F inverse are differentiable. So let's say this mapping X. So some X belongs to U. Let Y is be f of X. Now, inverse of Y, because of invertibility, F inverse Y exists, and they should send Y back to X, and when operated on X, it should again get back to y. And you can differentiate this. So we get differentiation of f of x, where x is f inverse y, and differentiation of f inverse of y. So because we are dealing with in R power n, so these are Jacobians. This should be equal to identity. So call this as 2f by 2x, and then this is 2x by 2y. Analogy, this is like 2f by 2x and 2x by 2y. So the key here is, and similarly, for x, any x of x, x maps, f maps x to f of x. If we do an inverse of this, we get that x. Now here x is in the domain, where y was in the codomain or range. So here also we have this f inverse of this thing. Let's call this by y, and do I by do x is d of f of x I. So with this 2, what we have is d of f inverse of y is d f of x whole inverse. Assuming this is invertible, d of f inverse of y is d of f of x whole inverse.